Okay, so what we're going to do is we're going to take two different cars and with each car do two different rotations per minute values and then calculate based on the initial and final speeds the angular acceleration of each car and see how it differentiates between the two different sized cars and different values of rotations per minute.
In our first trial, which was the Saturn at 800 RPM with an initial speed of 0 and a final speed of 6 miles per hour, we found out that it takes 25 seconds to get through the given displacement. In the same car at 1,500 RPM with an initial speed of 10 miles per hour and a final speed of 12 miles per hour, it takes 10 seconds to get through the given to that same displacement. And then in the third trial with the Nissan, which was at 1,000 RPM, the initial speed was 0 and the final speed was 10 miles per hour, and it took 18 seconds to get through that displacement. And in our last trial with the Nissan at 2,000 RPM, an initial speed of 18 miles per hour and a final speed of 26 miles per hour, it takes 5 seconds to get to that same displacement. All right, so first to find the angular acceleration, we have to convert from tangential velocity into angular speed. So to do this, we use this equation. And for the 800 RPM test, the initial angular speed is 0 because our velocity is 0. And for the final, our velocity is 6 miles per hour, which converts to 2.7 meters per second over the time, or over the radius, which is 0.30 meters. That comes out to about 9 radians per second. For the 1,500 RPM test, the initial is 4.5 meters per second over 0.3, and that comes out to 15 radians per second. And the final is 5.7 by 0.3, which is 19 radians per second. And then for the Nissan, which was 1,000 RPM, the initial for this is going to be 0 again, and the final, which was also 10 miles per hour, would be 4.5 meters per second over 0.34, which is the radius for those wheels, and that's 13.2. And for the 2,000, the initial is 8 meters per second divided by 0.34, which comes out to 23.5 radians per second. And the final for that is 11.6 meters per second over 0.34, which is equal to 34.1 radians per second. And to calculate the angular acceleration, we use this equation, and using this equation, we can find that for the 800 RPM test, 9 radians per second, which is the final, minus the initial, which is 0 radians per second, over the time, which we collected as 25 seconds, comes out to 0.36 radians per second squared. And that's for the 800. And for 1,500. This is with the Saturn again. It's 19 radians per second minus 15 radians per second over time, which was 10 seconds. That comes out to 0.4 radians per second squared. For the 1,000 RPM test with the Nissan, it was 13.2 radians per second minus 0 radians per second over the time, which was 18 seconds. And that comes out to 0.73 radians per second. And finally, the 2,000 RPM was 34.1 radians per second minus 23.5 radians per second all over the time, which was only 5 seconds. And that comes out to 2.1 radians per second squared.
So as you can see, with the jump in terms of 1,000 to 2,000 RPM, there was a much greater increase in angular acceleration than with the jump from 800 to 1,600. And our hypothesis for why that occurs is at a higher RPM, there's less energy required in terms of the gas, or provided by the gas combustion. So as you applied added energy to the system by the form of gas, you would increase the angular acceleration faster at a higher RPM than you would at a slower RPM.